Alright, let's say for example you've got two metals which normally if you were to place in solution wouldn't do anything. Like say for example I had a solution here, big bucket, and inside this bucket is nickel chloride, and so that means it's going to break up into its Ni2 plus aqueous ion and 2Cl minus ions. And of course these would normally be considered spectator ions, but actually they're not in this occasion, and I'm going to show you why. So if I get this and I have this solution of nickel chloride and I get this thing and I put it in here, and this is called a carbon electrode. It's an inert electrode. Carbon inert electrode, which means that it doesn't chemically participate in the reaction itself. And let's say I get something like copper. I have a, just so happen to have a cube of copper that I want to cover in nickel. Now if I dump copper into nickel chloride, nothing happens because nickel is above copper in the activity series of metals. So nickel can force its electrons onto copper, but of course it's in solution as Ni2+, so it's not going to want, it's got no electrons to force. And of course copper's not going to turn around and force its electrons onto nickel and go into solution because it's down under nickel on the activity series of metals. It's not actually possible for this to occur. And this is where you get your electrochemical reaction and you reverse the process. This is called a, let's see if we can get a bit more space here, voltaic cell. Oh wait, it's not voltaic, I'm pretty sure it's electrolytic. Okay, whoops. Voltaic cell is a galvanic cell. That's another word for galvanic cell. No, not voltaic cell. Electrolytic cell. E-L-E-T-R-O L-Y-T-I-C, electrolytic cell. Okay, this is an electrolytic cell. Hooray for terminology. Okay, so what have we got? We got this copper block here, and it's solid, and the copper, as I said, it does not want to come out into solution, so nothing happens. But what happens if we force the process? So instead of a spontaneous chemical reaction like what you get out of a, what do you call it, galvanic cell, you put a power source on here, and we're going to force this reaction to occur. And not just that, we are going to force the reaction to go this way. E minus, E minus, E minus. So all these little E minuses are going to end up going on the copper here. Now that's going to have a very, very special effect. The Ni2+ will want to go and collect the E minus. It'll be forced to because you're forcing these electrons into the situation. So you're going to get this half equation here where you get Ni2 plus aqueous plus 2E minus makes Ni solid, and you're nickel plating that copper cube. This is electroplating. This is how it's done. Now over here on this electrode here, something very special is occurring. You're actually getting bubbles of gas coming up, and it's going to smell like the pull, and for very good reason, because if the electrons are coming this way, then they must also be being pulled out of that way. And the way you look at it in this case here is, well, where are those electrons going to come from? Well, there's not many other sources of electrons. They're not going to get them from the nickel because it's already positively charged, so all that's left over is the chlorine. So in this case here, 2Cl minus becomes Cl2 gas plus 2E minus. I know that that's all supposed to be on one line, but I got the nickel chloride's got in the way. I'll just rub that out. Cl2 gas plus 2E minus, and those 2E minuses go up through the power supply. But this Cl2 gas bubbles out here and it actually makes chlorine gas. And you can see it, and you can smell it. Now the difference with this kind of reaction is you don't have it in half cells. You actually have it in just one cell. The whole thing. Now you still got an anode and a cathode, and oxygen and red cat still applies. So the anode, oxidation, reduction of the cathode. Now here we've got nickel receiving electrons and becoming nickel solid. So reduction is gain, so the nickel is reducing here. So this is the cathode, which would make this one the anode, which makes sense because the chlorine itself is losing electrons. So oxidation at the anode and oxygen red cat. And now you've got to also assign the positive and the negative terminals here. So in this case here, electrons flow